Now we are ready to look at the whole Einstein equation of the photoelectric effect. So previously we learned about the stopping potential, also known as Vs. I'm going to put here Vs. So what is the stopping potential? The definition that you need to know about stopping potential is that it is the minimum potential difference, okay, between the cathode and the anode, the minimum potential difference necessary to stop the electron flow in the photocell. Yeah. Or you could also say in a way that the minimum PD necessary to stop the most energetic electron from reaching the other side of the device. Okay, so there's a cathode, there's an anode. Now let's unpack this a little bit more. Let's say I have two plates. One will be the emitter, one will be the collector. Okay, I know it's supposed to be curved, but let's straighten this out a bit so our brain is not so tangled. So I am going to shine light on this plate. Zoom, 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 pew, light come in. A packet comes in. Maybe got more packet come in, but never mind. Got packet lah. Okay. Then what happens if, let's say the electrons come out. There's one electron I am going to put here. So electrons ejected from the plate. This is what I'm going to call the emitter, which what you looked at earlier. Then the collector is at the other end. But you can adjust the potential across the plate in such a way that, let's say this is the most energetic electron, most energy one, come out straight away, got very fast speed. So this one is coming out at a fastest speed among all the others, the fastest possible, Vmax. This is velocity, oh, don't confuse. Velocity. Then it travel, it reached the other end. Maybe it just barely reached this plate, but then it not enough energy and U-turn back. But at that moment when it has reached the other plate, you can say it stopped moving lah, V0. Why does it stop moving? What is opposing it? If you look very carefully, this is like a parallel plate electric field that we have learned before. So, where the electron want to go? Electron by default want to stay on the positive plate. It does not want to go to the negative plate because of an electric field set up in between these two, emitter and collector. So there is a change in kinetic energy happening here. So as you move, there is a decrease in kinetic energy as you move from left to right. But where does the energy go? Energy have to be conserved, right? Now don't forget you're climbing to a higher potential energy for this electron. So what happens is you're actually increasing your potential energy. So right here, increase in electric potential energy as you move across there. Oh, okay. So remember that there is a work done by electric field. When you have the emitter, collector, positive, negative charge, work done by electric field. And that amount is equal to the kinetic energy or the change in kinetic energy of the maximum velocity electron, the one that's moving the fastest. So you can think of it this way, it's a loss in kinetic energy, but a gain in electric potential energy. Do you remember the equations for this? Oh my goodness. Okay, let's go. See. So work done is what? QV, right? So QV. What is kinetic energy? Half mv squared. Okay, so you write half mv squared. But notice we are doing this for the maximum kinetic energy. And what V is this? Stopping potential, right? That's what we're looking at, stopping potential. So we are saying, okay, so this between these two plates, there will be a certain potential, V. Or potential difference lah. Potential difference. But you want to look for maximum maximum. So this one will have to be the maximum potential difference, also known as the stopping potential. So let's level up this final thing. So if this is Vs, then you have Vmax. Now this is the equation that we can use often to calculate the stopping potential, or use the stopping potential to calculate the maximum velocity of the electron that come out. Okay, so go back to the definition. The minimum PD needed, that is your stopping potential. What PD is between your emitter and collector, needed to stop the electron flow. Stop the most energetic electron. So if this one got the most energy, it's moving the fastest. But then it just stopped, like it does not touch the plate, but it just reached then that is when your V is 0 and then you turn back and come back. So that's your, just nice, you can adjust your setting in such a way where you can measure the stopping potential. Or know the Vmax, up to you lah. Okay, so no, this is how you can think of stopping potential. Another thing that you need to know to put together Einstein's equation is the idea of work function. Let's start off by defining what work function is first, the definition that you need to know for A levels. So work function is what we call the minimum energy required for an electron to escape. You can say bye-bye, escape a metal surface. Okay, that is the idea of a work function. Oh, now let's go and unpack this. What does this mean now? What exactly is a work function? Okay, so remember how we have metal plates? Like this one over here. Maybe you got some metal lah. Okay, I don't know what metal, but it's a metal here. Then you have an incoming photon that comes in with some energy. Boink, boink. And this one has some energy of, let's say, 10 eV. Now, there are all kinds of different electrons stuck inside the metal plate, right? There are some that are near the surface. There are some that are deeper down. And there are... Why did I draw a positive? Yeah. Not positive. There's some deeper down. And there are some that are really, really, really deep down inside there. So the minimum energy needed is how much? Which one you think can come out first? The one near the surface, right? So the minimum energy needed, maybe for this particular fella, you need roughly to go from where you are out and escape. Maybe you only need 1 EV. So this one 1 EV can escape now. The rest all need more lah. Maybe this one need 2 EV to get out. Maybe the other one need, I don't know, 5 EV. Let's put 5 EV. So what's the minimum? 1 EV. So for this particular metal, the minimum energy required for an electron to escape is 1 EV. That's what we call the work function of this metal. Right? So you can think of it this way lah. If you want to put an equation to it, what is the minimum energy of a photon needed so that 1 electron can escape? So you look and see, this one 1 EV of energy already can come out already. Very easy. Okay, so that means you only need 1 EV photon coming in, then you're good to go. Okay, this is a photon packet. So you can say that the work function, you can measure it in such a way where the energy needed is phi. We use this symbol phi for work function. And this E is what? Let's call this HF naught equals to phi. So this incoming photon is some, I don't know lah, we just call this some frequency F naught coming in. Then can come out. So that's how we define work function. No? So I'm going to rewrite this a little bit. Sometimes you can say work function equals to HF naught, or you can say, in terms of wavelength, how? HC over lambda naught. Wow, how do you get this from, Miss? C equals to F lambda. All this is not. So you just sub in. No? Don't forget this one from AS equation. So this is an idea of how you can use this equation for work function, which will be useful in solving question. Okay, what is this naught? Okay, let's label and see. So this naught here is what we call the threshold frequency or threshold wavelength. I'm going to write here, threshold frequency or threshold wavelength. If it's lambda, it is wavelength. There we go. Okay, and note that every metal has its own work function. So you look at this side, I scroll, I show you. Work function. See, aluminium 4.3, carbon 5.0, gold 5. Which one you think are the most work function? What is hardest to get electrons out? You look and see, wow, this one is the highest work function. Which is the lowest? Wow, this one's so low. So lowest means little bit of energy, electron come out already. Highest work function, carbon, you need to shine a very high frequency electromagnetic radiation, then only electrons can come out. And in fact, people will study this and they go and study all the different elements and see what is the work function. Depending on the type of element and their atomic structure, you will have a different work function. But in physics, we don't worry about this. We let other people go and do experiment. In A levels now, they will give you the work function. You just need to know how to use it. So back to the work function here. Now we are ready for Einstein's master equation that puts together all the ideas. Stopping potential, the work function, and this is called the photoelectric equation. So the main equation, the most important one you need to know for this whole section is this one. So Einstein put together all the parts and said, okay, this is the final statement. So, and a photon that's incoming have a certain energy. That is equal to the work function plus the maximum kinetic energy of that electron that comes out. The photoelectron that comes out. So this is the most important main equation. And we'll see how to use this in a bit. By the way, this is the idea of conservation of energy. Do you know why? Let's look at this diagram on the left side again. Let's say we have the 10 eV photon coming in. And then this 10 eV hit the first electron, 1 eV. So the electron receives 10 eV, but it needs to use 1 eV to get out of the metal. After it get out, then it can fly. Yay! And this fella will have a KE of 9 eV. Why? Because you receive 10. You use 1, how much do you have left? 9. So you come out, yay! 9 eV come out now. And this is your maximum. KE max. If your metal has a work function of 1 eV. How about the other fellas leh? If each of them receive 10. So they receive energy. Then the second fella use 2 eV to come out. So then this fella will come out with slightly less. 10 minus 2, 8. 8 eV. A little slower lah. Now this last poor fella stuck all the way inside the metal. Ayo, use 5 eV to get out of the metal. Okay, and how much left over do we have? 5 eV. So this fella will come out with 5 eV of kinetic energy. Which one got maximum? This one got maximum lor. Sorry, I cancel out. This one got maximum. Okay, so you see, the whole idea is conservation of energy. You receive energy, you use, and what is remaining, that is your kinetic energy. Okay, this is the idea of conservation of energy. So I'm going to highlight that. You receive, oh, that is big. You receive, you use, and what have you remain. That is the idea of this one. So you receive a certain energy, you use phi to get out of the metal, and whatever energy you have left, that is the remaining energy, which is kinetic energy. Now, every single term inside here is energy law. So the unit, all energy is either joule or in terms of EV. You see, I write all EV because joule is a bit long lah. So all this, every single term is energy, joule or EV. Okay, so remember this idea. The whole thing is conservation of energy. You receive, you use now, what do you have left? So in past year question, you will need to be able to use this conservation of energy idea and sub in all kinds of different things. For example, energy of photon. What are the other equations to calculate it? You can either think of, don't forget, E equals to HF, but also you can calculate with HC over lambda. Any of these can be used inside this equation. So you can sub in, then your equation become longer now. So I'm going to put a circle here to show that. Okay. Then the work function, work function, we just wrote this equation up there. So you can also use that sub inside here. Any of those, HF, HC over lambda also can. How about KE max? We looked at this previously. Work done by electric field. So here also you can sub in. Let's use a nice and light color. This one, kinetic energy, you can calculate with some other equation such as half mv squared, of course lah. Or you can use QV stopping. This is maximum potential. Maximum kinetic energy stopping potential. Okay, so this one, you can sub in more stuff. This one, you can sub in. And the other one, E photon, you can also sub in more things. Put all the equation together, so know how to use all of them. Don't memorize. Make sure you understand it. Another thing that past year can ask you to do, other than just plug in and calculate, which is bonus points, is they can ask you to draw graph Wow! Based on this equation, you can create so many graphs. So we're going to look at some example of graph, and you need to use your practical skills, y equals mx plus c, and all that thing to deal with this equation in all kinds of graphs. Okay, let's look at the first one. What if I give you a graph of kinetic energy max? Okay, this is the kinetic energy max against, should I put lambda or frequency? Let's put frequency. So kinetic energy max against frequency. And I say, oh, how does the line look like? You have to like, is it a linear? How to linearize? Okay, so now you stay calm. You look at the original equation. Where is Emax? Emax is inside here. Okay. Where is F? F of what? Incoming photon. Oh, okay. So you can do this. You write and sub in everything you know. So E photon, what do we know? HF. Okay. Work function is what? HF, but HF not for threshold frequency. Then the KE max you just put there E max. So we're going to rearrange this into a linear equation. So we have E max equals to HF minus HF0. Do you recognize this pattern? This is what we call y equals to mx plus c. You recognize it or not? Come, I label for you. So look, this is y equals to mx and a c. This is on the y-axis. Emax down here. I mean on the left side. X, might also put a bracket there to remind yourself, is the x-axis. Then anything else that's constant, that's going to be c. So this is a y equals mx minus c actually. And your gradient is what? What's the gradient? Look very carefully. Gradient is h for this particular equation and graph. So every graph is a little bit different. You need to know how to rearrange and have a pattern. So we know that it's going to be a straight line graph, and oftentimes Parser will give you a graph that looks something like this. But you can extrapolate backwards. You draw the dotted line yourself. Now, what is the gradient? What is everything? Okay, we just write here. So the gradient, firstly, is going to be m equals to h. So for this graph, for this one, if you take, you draw your triangle, find gradient. Gradient is going to be h, the Planck's constant. Oh, it's constant, so gradient will be constant no matter what you change. For this graph. And the y-intercept is what? Work function. So I'm going to label that down here. Work function, also known as, this will be a negative number. Your work function will be the intercept, and that in this case will be HF0 for that intercept down there. The last and very important one is the F0. This one. What is F0 again? Threshold frequency. Minimum frequency so that an electron can be emitted. Minimum energy needed. So from the graph, you can actually read the F0, and that is from, let's label it pink. Let's label it, I don't know. Okay. So this is F0 right here. On the frequency axis, that is when your KE is 0. Let's go back up to the diagram up there. Kinetic energy 0 means what? Threshold frequency. Okay, let's draw another electron. Let's say there's another electron so deep that it takes 10 eV to get up to the surface. When it reaches the surface, will it have any energy left? Not exactly. You use up all 10. So you use 10 eV just to get to the surface. So when you reach the surface, your energy is going to be 0. No kinetic energy remaining. So this is what we call the threshold frequency. When you come in with 10, if you have to use 10 to get up for a particular work function, then you come up no more energy liao. Poor fella. Okay? So that's work function. So you come up to the surface, you don't have any kinetic energy max for that particular metal, means that value is a work function. So that's where the line intercepts the frequency axis. That is your threshold frequency. Write that down. Threshold. Threshold. I cannot spell. So this is one way they can ask you things to note. Warning. Past years, they can switch the axis one, you know, so you be very careful. For example, they can tell you, hey, actually, I want to plot frequency here and Emax here. You must know how to rearrange your equation. Sometimes your Emax is in joules. Sometimes it can be in EV. When you're doing calculations, be absolutely sure you know what you are calculating lah, because your Planck's constant is in joules second. So I write here, warning number 2, unit. Planck constant is in joule second. So make sure you are in joule lah. Or you convert to EV, you use EV lah. So if you see EV, be very careful, must convert to joule first before you do any calculation. One last graph. There's too many examples to show, so I just pick one and show lah. Okay, let's say I throw you a graph of stopping potential Vs against frequency. By the way, frequency also can change. Sometimes I can say instead of V, I put 1 over lambda. Also similar graph, all the graph also same shape one. Frequency or 1 over lambda also can. So this stopping potential graph, we're going to look something similar, also a straight line. So how do you linearize your equation? Where do you see Vs in the equation up here? Your main equation, got Vs Don't have lah, but here got lah. So you might need to sub in this into K Emax. So let's do that and see if we can linearize an equation to find an equation for this graph. So let's start off. We know the energy of a photon is hf. Work function, want to substitute in okay lah, we substitute in hf naught. Then the last one, instead of Emax, now we're going to sub in QV, stopping potential. QVS. Now we have Vs in the picture. This is our y-axis. X-axis is F. So F is here. So we need to rearrange. By the way, quick note. The Q here is going to be E, which is the charge of electron, 1.6 times 10 negative 19 coulomb. Constant lah. Okay, let's rearrange. So I'm going to put EVS equals to HF minus HF naught. One more step. I only want Vs there. I want a straight line equation. So I divide H over E. Divide everything by E. So this is HF naught over E. The reason why I put bracket is so that I can recognize, oh, this is my y-axis. This is my x-axis. Everything else, this will be constant, a bunch of constants over here. And of course, lastly, the gradient. This will be my m. Y equals to mx minus c, or plus c, however you want to see it. However you want to see. Okay, so here you can also extrapolate backwards. Ding, 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 ding. What's the gradient? Gradient is going to be h over e. So we can label that out here. Oh, hey, now your gradient is different. Gradient is going to be h over e. Okay, now the same thing applies. Your threshold frequency here is still f naught. Or if your graph is in 1 over lambda, then this will be lambda naught. Also can. So, or 1 over lambda. Depends on what your axis is. So that is your threshold frequency. Now the intercept. Your intercept down here is your work function, which also can be written as hf naught over e on the negative part. So this is your work function. For the certain metal, each metal got its own work function. Sometimes they will ask you to talk about how the graph will change depending on the equation, what you sub into the equation. So we know Planck constant is constant. That one cannot change lah. Not normally. But what you could change is the work function of this metal surface. Maybe you change from copper to zinc to sodium, or something happened to your metal, it got ionized or oxidized, the element change. So you see, this is the graph of kinetic energy against frequency. So Ke max against frequency. So if I change the work function, I change the y-intercept. So the graph is just sliding up and down. What does that change? Of course, graph slide up and down. But you see, the place where this graph intersect the frequency axis, this here is our threshold frequency. The threshold frequency will change. See, I increase the work function, I make it more negative. Now the threshold is over here. Is there any electrons emitted? No. Nothing. But, because currently I'm at this red dot, but if I put the work function lower, so now the work function is much smaller, intercept is higher up, less negative. So this is the threshold frequency, and there are electrons coming out. Because why? We are currently at this position, and this one, you are more above from the you are higher than the threshold frequency lah, so you can have emission. See, all this place that I just show you, all this region is above the threshold frequency, higher than the threshold frequency. But work function change liao. Now you have not enough energy here. Oh no, so you need to go higher up past the work function. The threshold frequency, then only you have electrons come out. Okay, so remember, work function, you are shifting your graph up and down, and that will change the threshold frequency for electron to come out. Okay, so that's all the main things you need to know. Remember, the main player is this Einstein equation. Know how to calculate it, know what it means, okay, makes sense to you, and of course, know how you can manipulate this to create all kinds of graph, find gradient, find intercept, change gradient, change intercept. Okay, so that's all for this video. Now we are ready. Go check out some of the example video or try some past years to test your understanding and apply this equation in all the questions. That's all for this video. I will see you in the next one.